All right, so for this example, we have a crane lifting a Connex box. We're asked to solve for the minimum counterweight to put on the back of the crane to keep it from tipping over. So we have a series of vertical forces acting on our crane, and it's in static equilibrium and not moving. So the first thing we're going to do is define what are going to be our positive x directions and positive y directions. And then so what we're also going to have to do is define which direction of rotation is going to be positive, because this problem is going to require us to solve using moments. So for my notation, this kind of counterclockwise arrow with a plus in the middle, that is showing that counterclockwise rotation is going to be considered positive, or counterclockwise moments will be considered positive, and clockwise will be considered negative. That's just the kind of traditional right-hand rule description. You can use clockwise moments as being positive and counterclockwise as negative, and as long as you are consistent through solving your problem, you will still get the right answer. So again, when you're doing these problems, make sure you show which direction you're going to use as positive, and that will help you to be consistent through your problem solving. All right, so that's the picture we're given. We're asked to find the force of the counterweight. So interestingly, we have two unknowns, the force of the front support and the force of the counterweight, but we're only asked to solve for one of them. So that's going to come up a little bit later. So solution. So this is a statics problem. We have a crane that's in static equilibrium. So solving the same process we've used every time so far, sum of the forces in the x direction is equal to 0. And we look at our picture and we see we have no forces in the x direction, so that's not very helpful. So next up, sum of the forces in the y direction is equal to 0. So we'll just go left to right. We have an 8 kip force that's going down, so that's going to be negative. We have the positive force on our front support. We have a negative 20 kip force going down, and we have a negative force from our counterweight. So that gives us a single equation with two unknown variables, so we're not able to solve the problem, which means we now have to move into doing our third static equilibrium equation, the sum of the moments about any point, which is equal to the sum of distance times force, is equal to 0. So whenever we do a moment equation, we have to define a center point that we're going to measure all of these distances from. All right, so the easiest way to do this is to just pick the far left point as kind of our center point that we're going to measure all these distances from. And now we have to figure out which forces are going to create positive moments and which forces are going to create negative moments. So I think the easiest way to think about this is imagine that point that you've chosen your center as kind of an anchor point, all right? And the whole thing is going to try to spin around that. And so if that's our anchor point, our force from the front support is pushing up. So if you imagine this as kind of a lever arm, and you're pushing up on that side of it, that's going to try to create a counterclockwise spin. And then likewise, the 20 kip force is going to try to rotate it in the clockwise direction, and then the counterweight will also try to rotate it in the clockwise direction. So because over here I said that counterclockwise is positive, that means the front support is going to create a positive moment, and then the two downward forces are going to create negative moments. Okay, and then so for each moment, a moment is equal to a distance times a force. So that distance is the distance between whatever we've chosen as our center point and the force that's acting on it. Okay, so for the front outrigger or the front support, that distance is 40 feet. For the 20 kip force, it's 40 feet and then another 2 feet. So a total of 42 feet of distance. And then the counterweight is 40 feet, then 2 feet, then 12 feet, giving us a total of 54 feet of distance. So if we do our moment equation, and then for the 8 kip force, the 8 kip force is acting at the point that we're thinking of it rotating around. So the distance between the 8 kip force and itself is 0 feet. So if we do our moment equation, we have 0 feet times 8 kips, and then we have a positive moment of 40 feet times the force on the front support, and then we have a negative moment of 42 feet times 20 kips, and then we have another negative moment of 54 feet times the force of the counterweight. Okay, so at that point, now we have two equations with two unknowns. So if we wanted to, we could take our sum of the forces in the y direction equation, and we could solve that for the force on the front support and get that the force on the front support is equal to 28 kips plus the force of the counterweight, and then go ahead, plug that into our moment equation, and we get that 0 is equal to 0 times 8 is just 0. So that would give us 40 feet times, in parentheses, 28 kips plus the force of the counterweight minus 42 feet times 20 kips is going to be 840 foot kips, and then minus another 54 feet times the force of the counterweight. Go ahead, plug all that into our calculator, and we get that the force of the counterweight is 20 kips. And then at that point, we would be done. We've solved for the force of the counterweight, and that was the only thing that the problem asked us to solve for. But there's something else that we can learn from doing these moment problems. So I'm going to draw another picture because I'm going to re-annotate it. Right? So this is what our picture looked like. We had a couple forces, some up, some down, and we had two unknowns. We had an unknown on the front outrigger, and then we had an unknown counterweight force at the back. So when we did our moment equation earlier, we picked the far left point as our 0 point, and we went ahead and solved, gotten a moment equation. Now, if you look at that, though, you'll notice that when we did the sum of the moment equation, one of our moments ended up being 0. We had a point where we had 0 feet times some force, and it just canceled it out. So what you can do is you can strategically pick your center point for rotation to cancel out one of the forces, because you'll have that force times a distance of 0. So the strategic way of doing this is you look for one of your unknown forces. So for us, you pick one of your unknown forces that maybe you don't care about as much. So for us, that'd be this unknown front support force. And you say, hey, if I pick that point as the center point for rotation, my distance multiplied by that point will be 0. And so that'll make it go away from the moment equation. So there will be one less unknown in the moment equation. So let's see what it looks like if we do that. So if we pick that front support as our center point and imagine the whole thing rotating about it, now the 8 kip force is trying to create counterclockwise motion. The 20 kip force would go to clockwise, and then the force of the counterweight is also going counterclockwise. So that's going to be a positive moment, a negative moment, and a positive moment. So if we do sum of the moments around the front outrigger, that's equal to the sum of distance times force, which is equal to 0. So we start on our left. So we have our first force, which is 8 kips, and it is 40 feet away from the front outrigger. So 40 feet times 8 kips. Then we have the front outrigger itself, which is 0 feet away from itself. F front. So that is going to be 0 times anything is just 0. So then we have a negative moment from our 20 kip force, which is 2 feet times 20 kips. And then our last positive moment, 14 feet times the force of the counterweight. And if you look, now we have an equation with a single unknown. 0 is equal to 320 foot kips minus 40 foot kips plus 14 feet times the force of the counterweight. Oops, I'm sorry. I drew the counterweight force going up. The counterweight force is down. That means that it causes clockwise motion, which makes it a negative moment. Apologies. This is why you should never do math in public. Negative, which makes this guy a negative. That's better. Okay, so now if we were to go ahead and solve this, we would directly get that the force of the counterweight is 20 kips. And just like that, we've solved the problem and we haven't had to do any kind of substitution. So what I'm trying to show is you can strategically choose your center point when you're doing moment problems in order to eliminate one of the variables. The only thing you have to do is notice that the distances for all 4 of the forces were different than they were when we had a different center point for our center of rotation. So again, the biggest problem you run into when you're doing these moment problems is consistency. You have to pick your center point for rotation, and you have to make sure that you define your positive and negative moments correctly, and then make sure you define the distances correctly. Yeah, and that's all for this example, and there is another moment example after this.